Hey everyone. In this lecture we're going to be discussing angular kinematics, and to begin with I'd like to share a Calvin and Hobbes strip that I remember reading when I was very young, and I also remember my reaction being much like Calvin's. So let me just read this for you. So his dad walks up to him and says, "Playing a record? I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right?" And Calvin says, "Yeah." His dad goes on, "But the point on the record's edge has to make a bigger circle in the same time, so it goes faster. See, 2 points on one disk move at two speeds, even though they both make the same revolutions per minute." And this is him losing sleep over that idea, right? And I think that when I first read this, my reaction was very much the same. We'll see, right, that what his dad is talking about is basically the difference between tangential velocity and angular velocity. And we will discuss both those things in depth a little bit later on. The first thing we need to do is just get some definitions out of the way. Bear with me if you've already, learned about arc length, if you're familiar with this idea, but it is kind of important, and it's something that is traditionally introduced in a discussion of angular kinematics. So let's just define it, and then we'll unpack that definition a little bit. So I'm going to just write, for a circle of radius r, the arc length is given by, we'll say S, which is the arc length, right, equals r times theta, where theta is just some angle inside the circle, right, and it should be between 0 and 360 degrees. But we'll see that we actually have to specify theta in radians, and I'm going to kind of use this discussion of arc length to springboard into talking about radians. So let's check the dimensions of this before we do anything else, though. So checking the dimensions, we can write something like this. We can write that the dimensions of S equal the dimensions of a radius times the dimensions of an angle, right? And we know that the dimensions of a radius should just be a length. And I'll just keep theta inside the square brackets here for the time being. And I want to do this because, well, an arc length should have dimensions of length, right? Because, I mean, it's in the name. So what this tells us is that the dimensions of theta equal 1, right? I mean, that's kind of a strange thing, especially if we're very much used to working with angles in terms of degrees. So what there's an animation I found on Wikipedia that I think is pretty good for showing you how the arc length and radians are related. So let me just make this bigger here, and I'm going to wait for it to reset before I move it over to the other screen. Let me just reload it. That's probably the simplest thing to do. So they're going to draw a circle, right, of some radius. Then they're going to say, well, what if the arc length, and that's what's indicated by this red line here, right, the curved length, is equal to the radius in length? Well, that gives us our definition of a radian. And here they're just kind of showing you something you probably already know, but is that pi radians equals 180 degrees, and therefore 2 pi radians equals 360 degrees. So let's do a quick calculation here. This is going to be very quick, but we want to compute the arc length of a circle of radius big R when we're taking the angle to be 2 pi, right? And so applying the formula, we simply have that S is R times 2 pi, right? Which is 2 pi R. And this is just the circumference of the circle, right? So it's good that you know this is consistent, and that's obviously something we always want to check for whenever we have some new definition or idea, right? So the idea behind the radian is demanding that the arc length be, what do you say, of a given circle, because this is for any circle, right, not just a specific one, be equal to the radius of the circle. And so what this looks like, right, is we just say, well, S has to equal R now, and R equals R theta, so therefore theta equals R over R, which is of course 1, and this is what gives us 1 radian. And so a radian is simply the angle subtended inside a circle when the arc length equals the radius of the circle, right? And by convention, the radian is not actually like a real unit, and it doesn't have dimensions either. But when we write it, we will often write, let me just say this, we'll often write things like theta equals, like, I don't know, like 2 pi thirds or something, right, radians. And this is fine. And this, I think, is mostly it's mostly useful when we're actually like plugging angles into trig functions, because your calculator is going to care very much if you're in degree mode versus radian mode, right? And so writing the rad is a good idea, and I will try to remember to do that as often as I can. And so let me just say this: the conversion factor from radians to degrees is pi radians equals 180 degrees. And that's really all you need to know. Is like, if you don't really understand anything else about this, it's just another way of expressing angles. So that's that, right? So now I want to begin with remembering or reminding you what the linear kinematics equations look like, right? And so I'm just going to copy and paste those, because I think by now we're all pretty familiar with these. And so these, I think, in the form that I gave them to you, look like this, right? You have the x position as a function of time, and we're talking about one dimension here, right? The velocity as a function of time. I didn't write subscripts on like the v's and a's just to save a little bit of time, but obviously this is all referring to something that's happening in the x direction. And that's it, right? And so remember that in linear kinematics, we're interested in, say, like the position of an object or its displacement, its linear velocity and its linear acceleration, right? And so what we're going to do is we're just going to adapt these equations to the angular case by analogy, right? That's all this is really going to involve. So basically what you'll see is that we're just going to translate them to Greek, except t will stay t, it won't become tau, but everything else. Okay, so what I want to say is that if in linear kinematics we're interested in the position of an object, then in angular kinematics we're interested in the angular position or displacement, right, of an object. And we can think of this can be thought of as how many radians something that is spinning has subtended, right? This is just a fancy math word that basically means turned through. Right, so if you're standing, right, and you basically just turn around so you're looking the opposite direction, you were before, then your angular displacement would be pi radians, right? Because you haven't gone a full circle, you've just gone a half circle. And if you turn all the way around, right, so you do one complete rotation and you're now looking in the same direction you originally were, then you've gone through an angular displacement of 2 pi radians, right? So let me just say this. I want to say then an angular displacement can be defined as essentially a change in the angular orientation of something, right? I think that probably everybody has a kind of an intuition about this stuff, especially, I don't know if you've ever like had somebody spin you around in like an office chair or something, you know, and tried to walk. It's, I don't know, it can be a lot of fun. Anyway, so that's an angular displacement, or that is angular displacement. Let's talk about angular velocity. And before I move on, I should just say this is going to be our symbol, right? This is theta for angular displacement or angular position. And what we will use for angular velocity is omega, right? It's not a W. Please don't call it a W. It's omega. You know, interestingly enough, I have a very bright friend who's doing his PhD in physics at Northwestern, and I think he still calls it W, but he's definitely an anomaly. So just remember, it's not W, it's omega. Anyway, so let me just say this. Remember that in linear kinematics, the velocity of an object tells us the rate at which its displacement is changing, right? So in angular kinematics, the angular velocity tells us the rate at which the object's angular position or displacement, right, is changing. So we can write, and this is just going to be the almost the exact same thing that we had for linear velocity, right? Except we're going to have a delta theta on top instead of a delta x, but it will still be over some time interval, delta t, right? And I'm just going to say similar to, and remember that we defined, for instance, the x component of velocity to be delta x over delta t when we were talking about linear kinematics. Okay, so I think you probably are starting to get the idea here, and we're just going to do one more of these, and we're going to talk about the angular acceleration. And so let me say, finally, if the linear acceleration of an object tells us the rate at which its velocity is changing, then the angular acceleration tells us the rate at which an object's angular velocity is changing. Then we can write, in, you know, with a lot of resemblance to what we wrote for linear acceleration, that the angular acceleration is given by, and now we write delta omega over delta t, okay? And so I think we're now in a position to just state what these equations all end up looking like, right? And so I'm just going to copy and paste them from the other document here, because it would be a lot to type. But we just essentially make the transcription that, well, wherever we see an x, we change it to a theta. Wherever we see a v, we change it to an omega. And wherever we see an a, we change it to an alpha. So I know it's probably going to take you a while to copy these down, as opposed to, you know, the mere seconds it took me to copy and paste them. So I'll just talk about these for a little bit here. So this is the angular position of an object that's spinning, right, as a function of time, essentially. Usually theta naught, omega naught, and alpha will be our constants, and so it's just a matter of, like, if you know all those things, plug in t, you're good to go. Same kind of thing goes for this second equation that I have boxed here. This just tells us the angular velocity of an object. If we know the initial angular velocity, its angular acceleration, and the amount of time that has gone by. This same thing, right? But this one here, this has no time dependence, so there are lots of situations in which that's useful. And then this one down here really comes back to the idea of like an average velocity, in this case an average angular velocity, right? Because we will always be dealing with constant angular accelerations, and so we can just take the average of the initial and final angular velocities to get the average angular velocity, right? And so that's that. I mean, it's just as simple as this. Now, there are some details that we have to discuss, of course, right? To make sure that we're able to use these to solve problems effectively, but it really just comes down to, like I said, translating our linear kinematics equations to Greek, except for t. That doesn't become tau, right? And I know that, x and theta aren't analogous in linguistic terms, right? But I think you see what I'm saying. Okay, cool. So let me just say, we have an example to do here, but what I want to say is that because angular velocity is a velocity, it must be a vector, right? And the way we determine its directionality or orientation is with the right-hand rule. And I should say maybe a right-hand rule, because there are two now that we have, right? Remember, we had the one for cross products, and now we're going to have this one. So this is a little sketch of what it looks like to apply this. And so imagine we have like a disk, say, that's just rotating at some, or with some angular velocity. You just curl your fingers in the direction of rotation, right? The fingers of your right hand, of course. You can't use your left hand, even if you're a lefty. And your thumb then, right, assuming that you keep it more or less perpendicular to your palm as you're doing this, is going to tell you the direction of the angular velocity vector. And I will put in words here our convention, right, because this is something that's important to remember, especially when we're talking about angular accelerations. I'm going to say that our convention is that when something is rotating clockwise, its angular velocity will be negative, right? And this is kind of opposite what you would expect, because, I don't know, at least for me, I always think, well, clockwise, yeah, that should be positive, because that's the way every clock rotates, but I don't know. So rotating clockwise means negative angular velocity, and when something is rotating counterclockwise, its angular velocity will be positive. And this is very much like what we did with one-dimensional kinematics, where if we wanted to say something was moving to the left, we would say, oh well, it's velocity is just negative something, right? And if it was moving to the right, say along the x-axis, its velocity was positive something. It's the exact same thing, right? And so this is like a little bit of math here that's not super important, but I do feel like I should say it. And I'm going to say that often we will simply define our positive z direction to be the direction in which the angular velocity vector is pointing. So for the image above, we could write, I'm going to copy and paste this from my notes here, but it's just, you know, a rehash of basically how we can write vectors. And so here I'm saying, well, it's just the magnitude of omega times z hat, so we've specified that it points up. And here I'm writing it as an ordered triple with the x and y components being 0 and it fully aligned in the z direction, right? And all of these ideas, I'm going to say all of these ideas also apply to the angular acceleration vector alpha. So now we're going to look at an example of this that hopefully might clear this up a little bit if it's hazy. And this is like pretty similar to something I had you do, I think, on like the very first quiz, if I'm not mistaken. And we're just going to look at these pictures of different angular velocity vectors and different angular acceleration vectors and see what's going on with the speed, right? The magnitude of the angular angular velocity vector, right? So for each of the following cases below, determine whether the angular speed is increasing or decreasing. So this really just comes down to the orientation of the angular acceleration vector with respect to the angular velocity vector. And so if we just imagine that our z-axis is oriented vertically, right? So positive z points up and negative z points down, then for the first case we can write something like this. We can write, well, omega is greater than 0 and alpha is less than 0, i.e. omega is positive and alpha is negative. So the angular speed is decreasing. Okay, and then for B, right, now we have a positive angular velocity, and a positive angular acceleration, so the angular speed is increasing. For C, it's just kind of the opposite of the A case, right? And now we have that alpha is positive, and omega is negative. And again here, the angular speed is decreasing. Finally, you probably see this at this point, but now they're pointing in the same direction, right? So we have that omega is negative, alpha is negative, and therefore the angular speed is increasing. Let me just make sure I wrote this all down correctly because sometimes my fingers and my mouth do opposite things. So looks good, increasing, decreasing, increasing. Cool. Okay, so that's good. If this is not clear, just maybe pause the video and take some time to convince yourself that it is. But again, this is like almost exactly the same thing as the quiz question that I asked you, where I told you, say, the x component of velocity is positive or negative, and the x component of acceleration is positive or negative. Like, how do different combinations of those affect the speed, or what do they say about the speed, right? Okay, so what we want to do next is kind of like relate the tangential velocity of an object, right? So this is basically a linear velocity to the angular velocity. And this is done with a cross product, right? So I'm going to say the tangential linear velocity of a point on an object, right? It's like, let's say you have a globe and you find Pittsburgh on it and then you spin the globe around. What we would be solving for here is like the tangential velocity that point on the globe has. And so I'm going to say the tangential linear velocity of a point on an object that is undergoing angular motion is given by, and as I said, it was a cross product, right? So in the interest of saving a little bit of time, I'm just going to copy and paste this from the other document. and it's given by this. And this, so I wrote perpendicular here, but you could also call this tangential, right? And I'll kind of use the two terms interchangeably. I like writing the perpendicular symbol in the notation, but I also prefer to call it tangential when I speak it. So hopefully that's not terribly confusing to anybody. And let me just say, I think that we have an idea of what the V denotes and what the omega denotes now, but the R I just want to specify is, so R not in bold, is the vector that takes us from the axis of rotation to the position at which we want to calculate the tangential velocity vector. And what I want to say is that like 9 times out of 10 for us, unless we have some like complicated three-dimensional situation we need to analyze, which I don't think we'll really do, let me just say this expression often becomes, and now we're just going to talk about the magnitudes, right? So the magnitude of the tangential velocity, i.e. the tangential speed, is just given by r omega. And perhaps you can see from the definition of the cross product that this happens when the angle between the r vector and the omega vector is 90 degrees, right? Because remember, the cross product depends on sine, and sine of 90 degrees is 1. So this is probably what we'll end up using most of the time on this, for this. And what I want to do actually is also just introduce this idea of the period, since I think seeing this makes it very, hopefully, easy to understand, but we'll see. So let me just go off on a little aside here and say, okay, so imagine that we have some particle that's like maybe moving in a circle, right? So it's not spinning about its own axis, but it's undergoing, say, uniform circular motion, okay? I'll just put this. So imagine a particle undergoing uniform circular motion. So as I said, it's not spinning about its own axis, it's moving around in a circle, right? We could say maybe in the xy plane. So to travel through the entire circumference of a given circle, let's say of radius r, it must travel a distance of the circumference, right, which is just 2 pi times the radius, okay? And if it does so in time t, then similarly to how, again, v sub x, right, can be defined to be, well, I shouldn't even say just x, but like in general, of velocity can be defined to be a displacement over time, right? But I'm just going to say x to be definite. We can write something like this. We can write that the perpendicular speed is given by the distance it must travel, right, the particle, divided by the amount of time it takes. But remember that we can rewrite this v sub perpendicular as just r omega, okay? And we already wrote out what the circumference was, and that's 2 pi big R. And then we divide by big T, which we'll just say is what we're going to call the period, right? The time for one complete revolution. Then, solving this for T, we have, it's 2 pi over omega. And this is the period. you can symbolize this different ways. I think the other common way is to represent it with a tau. So however you want to do it really doesn't matter, as long as it's like some sort of symbol that is usually used to indicate a time. And I just want to stress that, because I often use big T as just like a specific time when I'm trying to solve a problem for all of you. And so we hadn't really talked about angular kinematics at all up until this point, so obviously any big T that I've used in the past, there's not really a correspondence to this big T symbolically. Okay. So let's check this, right? For an object with constant angular speed. And remember that one of our kinematics equations told us theta as a function of time, right? And so I'm going to just rehash that here. I'm going to say because delta theta equals theta evaluated at the period, which is omega times the period, we find that delta theta equals omega. Now remember, we just found big T to be 2 pi over omega, right? And so we see delta theta in this case is 2 pi radians, I guess. And so this tells us, right, that this means exactly what we think it means, which is that it's the amount of time for an object to basically undergo one complete revolution. Okay. Cool. Hopefully that's clear. Now we're going to talk about tangential acceleration, and I'm just going to say, because this is defined very similarly, or I would say it's defined in the exact same way, really, as the tangential velocity. Let me just write the definition. I'm going to say this is defined to be, and this is also a cross product. And as with the tangential velocity, this will often work out to have magnitude. And I'm going to say A sub perpendicular equals R alpha. Well, I'm wondering, did I write it? No, I did. Okay, cool. Okay, so that's cool. And we'll look at an example of both these ideas, just so hopefully it becomes a little clearer. And so what I want to say, though, before we do any examples, is that we can note that this means, for instance, if an object is undergoing uniform circular motion, we can write the total acceleration of a point on the object as, and this doesn't have to apply just to uniform circular motion, but I think that in practice, when we use this idea, it will be for cases that involve uniform circular motion. So I just figured I would put that in there, but it is more general than that. We can say that the acceleration, the total acceleration, right, which I'll just call it A, is given by the vector sum, and I'm going to change these to vectors in just a second here, of the tangential acceleration vector and the centripetal acceleration vector. So formatting this the way it should be formatted, it ends up looking like this. Now I also want you to remember that for uniform circular motion, right, the centripetal acceleration of an object was given by, and we had that it was, well, the magnitude was v squared over r, right? But now with this idea of going back and forth between, and this was the tangential velocity, right? This v that we had when we introduced this idea. I think I probably wrote it like v sub t or something, but I'm just going to leave it as a v for now. But this is the tangential, I should say, tangential speed, right? Because this is not a vector as I've written it. Anyway, let's substitute this, where was it? This thing into the equation for the centripetal acceleration and see what happens, right? So up here, we're going to have r omega quantity squared. Down here, we have r. And so what happens is we get r squared omega squared in the numerator, and we have one factor of r in the denominator, so this becomes r omega squared. So this is just another way, now with this idea of angular velocity and angular speed, that we can write the centripetal acceleration of an object that is undergoing uniform circular motion, right? Okay, so now let's look at some examples of this. Okay, so common thing to consider for angular kinematics, and actually we're going to be looking at many, many more merry-go-rounds, I'm sure of it, but is the merry-go-round, because this is, you know, something that I think everybody's probably familiar with. Just in case, I guess, like I can show you what this looks like. Let me just do a quick image search here. Actually, not what I had in mind. Okay, this is what I had in mind. This thing. I would consider this more a carousel, but I don't know if that's correct. But like this, you see these on playgrounds and stuff, right? You know, like kids like to play with them a lot because I mean they're kind of fun. You know, you can like get really dizzy and stuff. So that's cool. Anyway, in the problem, okay, so a merry-go-round with radius of 2 meters is spinning counterclockwise as viewed from above with angular speed omega naught equals 10 radians per second. Because of internal friction, its angular speed is decreasing at a constant alpha equals 0.5 radians per second squared. How long will it take to a stop, or how long will it take to come to a stop, and through how many revolutions will it have turned once it has completely stopped? Now, before we even begin solving this, what I want to say is, note that I wrote its angular speed is decreasing at a constant rate, right? So what this means is that, thinking back to like the orientation of the angular velocity vector and the angular acceleration vector, well, we can just scroll up there. And what this would look like if we wanted to draw them in is perhaps like this, right? This first part here, the figure A as it's called, where they point in opposite directions. So we see, right, that the angular speed in this example that we're about to do is decreasing. And I'll show you what that looks like as far as, you know, doing the algebra and stuff goes, but it's exactly the same thing that we would do for one-dimensional linear kinematics. So I'm going to say the equation we want to use is this one, all right, omega as a function of t is omega naught, and I'm going to write minus alpha t. And this just means that I'm taking alpha to be a positive number, right? And so I'm indicating with the sign here that the initial angular velocity vector and the angular acceleration vector point in different directions, right? And as I said, this is exactly what we did in one-dimensional kinematics. But you could, I'll just say this, I guess, if you want to do it this way, you could write it with a plus sign and then say that alpha is negative 0.5 radians per second squared. And the math works out exactly the same, right? And that's why that is an okay thing to do. But I'm going to stick with my convention here. Okay, so if we, and I'm going to do it right now, I'm going to say, okay, so identifying, maybe I won't. I'll try to restrain myself here. I was going to use a big T, but let's just call it tau, I guess. We'll say identifying tau as the time at which it ceases to rotate. We have, and we could write omega of tau equals omega naught minus alpha tau. And so all we have to do is just solve this for tau, right? So then we find that tau should equal omega naught over alpha. And the reason this is, I should have mentioned this, but remember that this is because we're saying that omega at tau equals 0, right? So what we're really focusing on is this part of the equation that we wrote down. And so we find, after doing the algebra, that tau equals omega naught over alpha, and you should find numerically that this is 20 seconds. And note that if you had written the radians here in your units, they would cancel out. So it's kind of like they were never there, right? Cool. Okay, so for part B, we want to figure out basically what its angular displacement is after the 20 seconds has gone by. And so I'm going to say that we could do this two ways, right? As is often the case in physics. I think as we've seen by now a few different times. So the first way is with the equation, and it's going to be this: theta of tau equals omega naught tau minus 1/2 alpha tau squared. And notice that I didn't write the theta naught, but I don't think that this is particularly surprising, because remember that back when we were talking about kinematics, we had this idea that we could always take our origin to be where we wanted it, as long as we were consistent with that choice, and the same thing applies here as well. So we can just omit that, and it doesn't change anything. And so what you should find here is, numerically, I think it works out to be about 100 radians. Now we want to convert this to revolutions though, right? Because we're asked how many revolutions, and I don't intend to be annoying about this moving forward, but I think you should have like seen radians converted to revolutions at least once. So I'm going to do this. So we say to convert this to revolutions, we note that 1 revolution is just 2 pi radians, right? Because 2 pi radians takes us through a complete circle, and so does 1 revolution by definition. And so we just, what do we do here? Well, I'll do it formally like this, and I'm going to use the conversion factor. So I'm going to say 100 radians, and we just multiply it by the conversion factor, which equals 1, of course, despite how it might look, which is 1 revolution, right, is 2 pi radians. And we find that the radians cancel out, which is good. That's part of the reason we do it this way, so we can clearly see that cancellation. And this should, I think, work out numerically to be about 15.9 revolutions. So that's cool. The thing is spun around about 16 times in 20 seconds. Okay, I'm not going to do it the other way, but I'm going to show you how you would go about this, and then you can try it for yourself. So the other way to do this would be to apply, and we would want to use this equation now, omega squared, equals omega naught squared minus 2 alpha delta theta noting that omega squared, right? The omega that we care about is 0 because we're thinking about how long it takes for this to come to a stop, and noting that omega squared equals 0 because omega equals 0 at 20 seconds. So give this a try for yourself. Make sure that you get the same answer, and it'll be a little bit of extra practice for you. Okay, so now we're going to look at the total acceleration that you would experience if you were on the merry-go-round at a time of 10 seconds, right? And so this will give us a little bit more practice of figuring out what the angular speed is. So let's say at t equals t naught, the angular speed is, and we're going to use the angular kinematics equations again, so it's omega of tau naught equals omega naught minus alpha t naught. I think I might have said tau instead of t, but I wrote the correct thing here, so that's hopefully okay. Then, right, from that idea we discussed where we can relate the angular acceleration to the, actually, you know what? I shouldn't say then. Well, let me do it this way. I have it backwards in my notes. That's why I'm confusing myself. So I want to say then your centripetal acceleration is, and so we just use that formula that we derived earlier, where it was r times omega squared, right? And if you're at the very edge, I should have said you're standing on the very edge. Geez. Same merry-go-round from the previous. So, oh, I did say it. Wow. I'm tired. Okay. Let me just get rid of that. Pretend it never happened. I said it here. Anyway, this isn't about who said what, right? This is about doing physics. So the way we would write this is then it would just be like r times omega evaluated at t naught squared, and we would find then that this is r times, and I'm just going to copy and paste this. This is what we found, right, from the kinematics equations, and we just have to remember to square this. Now, this is where it can get a little bit tricky, because if we want to find the total acceleration vector, we need to make sure that we're being very careful about the sort of directionality of all these vector quantities that we're thinking about, right? Because the centripetal acceleration is a vector, and the tangential acceleration is also a vector. So what I want to do really quickly is just make like a sketch of this, and I'm going to use the tablet and do this like from the overhead perspective. So this is the top view of the merry-go-round, right? And it has radius r, and let's say you're standing here maybe, right? Like at the very edge. So what we can do is we can just use our normal x and y axes here. This could be one way that we would express the vector nature of these things, right? And so remember, centripetal means center seeking, so the centripetal acceleration points towards the center of the circle, like that. And so this would be our centripetal acceleration. And notice in this problem, the angular velocity vector would be pointing out of the screen, like right at your face, because from the right-hand rule for the Cartesian axes in 3D, we have to have, for instance, this is just a little math aside, but we have to have that x hat cross y hat equals z hat, right? So z hat is, like, if you imagine a little arrowhead pointing right at you, that's maybe what it would look like. And this is because we use right-handed coordinate systems predominantly. Actually, I've never seen anybody use the left-handed one, but maybe people do. But anyway, that's like the way that you might go about simplifying the geometry here, because remember that from the definition of the cross product, if your r vector and your, let's see, let me just say this. If two vectors lie in the xy plane and you take their cross product, then you're going to find that, and I think that I actually wanted to mention this for the tangential acceleration, but regardless, right, for two vectors that lie in, say, the xy plane, their cross product will point either in the positive or negative z direction if it's non-zero, right? And so let me maybe make another quick sketch here and just kind of show you what the r vector looks like in this case. I don't want the drawing to get too busy, but this is the exact same carousel, right? And what your r vector would look like for the next part is this. We'll call it r, like that. Okay. And so let me just move this off to the side. We'll look at the other part here. But before we do that, we can just say something like, well, if we want to define our x and y axes as I did, then we can just say that this points in the negative x direction, right? So let me put an x hat in there. There you are, the hat. And so you could rewrite this if you just want to pull the negative sign out like this. Let me remove those and then just put the negative sign in front of the whole expression here. I think this would be the most standard way of writing this, okay? So, and what I meant to write is that this would be the centripetal acceleration vector. Like that. Okay, cool. I think we're done with this part now. Okay, so then we wanted to look at the tangential acceleration, right? And the way that we would do this is, let me just say, for your tangential acceleration, we can use that a perpendicular is just, well, the magnitude of it is just r alpha, right? And we don't really even need to, I think, appeal to the math to see what this looks like. So I'm going to come back to the picture here in a second, but I'm going to write that this vector could then be expressed as r alpha y hat. Like that. And this is a vector. Okay, cool. And so, coming back to the drawing, what the perpendicular acceleration vector or tangential acceleration vector would look like is this. Okay. And let's, or wait, no, it wouldn't look like that though, because it would be the other way, because, okay, so here's what I'm thinking. Let me get rid of that, because that's not correct. I don't want to erase the whole thing. I just want to get rid of this and this. So actually, thinking about it sort of intuitively, the way that it should point is like this, right? Because this thing is rotating counterclockwise, but we already said that its rate of rotation is slowing down, right? And so I kind of tempted to try to draw this, but it would be very, very tough. But remember what we said about the angular acceleration vector, say, pointing down. So I will try to draw this. I'm going to draw now the side view. And I promise that in general this won't be so tricky, but I did want to just show you what these things look like as vectors. But if we're talking about the side view now, maybe. So now it's like we're looking at it from the side. Let's see, what would we be? We would be at z equals 0, right? This would be like our eye level is at z equals 0. And so remember that the r vector looks like this in the side view, and the angular acceleration vector looks like this. Okay? And so cross product of, was alpha r, right? Yeah. Cross product of alpha r should point as I've drawn it. Here. So it actually would be in the negative y direction. So let me fix that real quick. Thankfully, it's easy because I just have to put a negative sign in front of what I had written from before. Cool. So you have to be careful with this stuff, right? Because working with the vectors can be tricky in 3 dimensions, and this is in some ways kind of necessarily a topic that involves some discussion of 3-dimensional coordinate systems. Okay, but I think we'll do our best to sort of obscure that, so hopefully it doesn't confuse anybody. Okay, so then the final thing to note here, though, is just that your total acceleration vector is then just the vector sum, right? It's just, I'm going to call the total acceleration A, and stick with my previous notation for the tangential acceleration and centripetal acceleration. And what you could do, I don't think I'll calculate this actually, but I will just maybe express it as a, I did calculate it. I'm not going to calculate the numbers is what I'm saying. Just want to express this as maybe like a column vector like this, right? So this position is x hat, this is y hat. And what we would have then is we would have, this only has an x component, the centripetal acceleration, right? And this only has a y component. And so these are indeed perpendicular to each other. And I'm just going to say the magnitude of this vector could be computed via, and I'm going to copy and paste this from my notes here, but it would work out to just be this if I fix the sign. And we would just do this with the Pythagorean theorem, right? Just like any other vector. So this would be our magnitude, and you can, if you really want to, you can calculate the number, but I'm not going to do that. Anyway, that is it for this lecture. Hopefully this was clear. If not, of course, you can reach out to me with questions. The next topic we'll get into will actually be torque, where we're going to basically figure out what Newton's second law looks like in the angular domain, let's say. And so in particular, the idea of angular acceleration will be important, right? Because if we remember that for the linear formulation of Newton's second law, it's that the net force equals a mass times a linear acceleration. We expect Newton's second law in the rotational case to probably depend on an angular acceleration. And so we will talk about that in the next video.